And also, well, on the topic of starting, it's my pleasure to introduce Martin. Martin was my boss for until like a couple of months ago. I just escaped. Yeah, so of course, Martin is known as creator of Scala, and Scala has been is now leading the charge in the development of capability system using its strong type system, and I think Martin will talk about all of that. So thank you, Martin. I leave the floor to you.
The first question to ask, of course, is, well, why would we be interested in capabilities specifically for Scala? So what is Scala? How would I characterize it? Well, in a nutshell, I would say it's a mostly functional, expressively typed language that combines safety and convenience. That's what it wants to be, anyway. And that mostly functional part is not a compromise. That's exactly how it was designed. The idea was we use functional where it makes sense, and it makes sense in a lot of situations, certainly. And we use imperative where that is simpler or more efficient. But there's a dilemma with these mostly functional languages that Scala shares with other languages in the space, let's say OCaml. The dilemma is that immutable variables and other effects are convenient. It's very easy to just put a print-on statement in the middle of your function to figure out what goes on. It's very easy to just essentially have a side channel where you accumulate something instead of essentially going through a big data structure with a fold and so on. So used responsively, they make code cleaner and more readable and also more performant. But arbitrary side effects, arbitrary global changes, let's say, to the program are certainly not safe. And that's a dilemma because ideally, programming languages should guide programmers towards good behavior, towards good coding style. So that ideally, a program that looks simple on the surface is also safe and predictable. But with effects, that's not always the case. The simplest and maybe even most readable version is actually not very safe. So using side effects like vars or exceptions can make programs shorter, but also harder to reason about, in particular when we mix it with aliasing. And that's why adding simple, direct style effects in Scala is sometimes frowned upon. It's just too easy. It's too easy to do things that might be problematic later on. So that's why often people in the Scala community are outright scared of writing mutable var. That's just not to be done. They jump to great hoops to avoid it, even where it would be harmless. But they have this reputation to be sort of danger territory. So in a sense, Scala programmers, they like their guardrails, and they're faced with the uneasy choice that it could be convenient and fast but unsafe, or safe but complex and slow. And many pick safe and complex and slow, and those that pick convenient and fast, they feel like they have done something bad. So effects are, of course, a reality. We have them. So how do we attain them? And the popular answer so far is staged effects. So we typically have a pure functional program that constructs an effectful program expressed in a library. The slogan you hear about that is computations are values, and the constructing part is referentially transparent. So most interesting stuff then, the stuff that actually does things, is done in the libraries rather than in the language proper. So libraries like that exist in Scala, like Catsifact, FS2, Zio, there are many others. The downside is that to be fluent in the language, then you needn't know just Scala. That's not enough. You need to know these libraries, which are often an order of magnitude more complicated than the base language itself. So it takes I think it takes quite a short time to learn the basics of Scala, but it takes longer to learn the basics of essentially the type level stack or Zio or Akka HTTP or something like that. So if we make a picture of that, then the way we can represent this is to say, well, computers can do lots of things. They have mutable state, they have resources, transactions, errors, networks, everything, communication with the outside world. But we we prefer to program in this sandbox in a purely functional way. And then if we want to reach out and do the effects, then that is essentially gets mitigated by the fact that what we construct is a stateful program in one of these monad libraries that does these things then for us. So at least in the first stage of programs, we can say, well, everything is functional and referentially transparent. The problem, so here to summarize, what the computers can do everything, and the program, in a program, we restrict ourselves consciously to essentially the pure functional subset. The problem with that is it's not so convenient. Typically, this monadic form, it's clunky. It gets worse when you mix several monads, because then you have to go to something like MTL or monad transformers or tagless final and things like that. They're very heavy abstraction patterns that you have to follow to do that, and the code just gets, in my opinion, pretty ugly and pretty dense to understand. The alternative that we are proposing is a capability-based architecture where we say, well, we still have the system, computers can do everything. If we would just let you get at all of these things, we would be back to imperative programming. Let's just use the full capabilities of your computer. We don't do that. We say, well, except in the pure functional subset, everything else, you need a key, a capability to access these things, and that key is given to you typically as a parameter, that somebody passes you the key to say, well, you can use this resource, or you can produce errors in this way, or something like that. So access is controlled by fine-grained capabilities. In a sense, there's not a big deal, not a big difference when it comes to functional programming. In both cases, we have a clear delineation between what is purely functional and what is not. In the first case, that was just the first stage of our program, and here that would be a function that doesn't take or get any capability from somebody else, is necessarily a pure function. So in both cases, I have a type systematic characterization of what purity is. Another thing that often confuses people is to say the capability version can make non-functional effects safe, but they don't perform the effects themselves. So some people say, well, let's say, Cat's effect can do or Zio can do, well, it can suspend your program and do massive concurrency and asynchronicity and things like that. Can you do that with capabilities? And the answer is, well, no. The capabilities is just a key to a possibility to a resource that needs to be in the computer itself. So the runtime needs to be able to do these things. But runtimes are getting better recently. So, for instance, if we look at reactive and asynchronous programming, then we now have virtual threads on the JVM. We have continuations in Scala'25, and even on the JavaScript platform, we have WASM, which allows essentially JavaScript promise integration, which is sort of a very limited form of stack switching, and there might come more general stack switching is in the works. So we can hope that this will be solved there as well. Okay, so capabilities, what are they? In fact, capabilities are a really old idea. It comes back from 1966 by Jack Dennis and Earl van Horn. And they are just regular program values, but they're restricted in how they can be passed around. So they can be created, they can be passed to other objects and their constructors, and they can be passed to methods and messages. That's all. So the advantages of that is there's no new feature at all. That's just what you can do with normal variables. In fact, what we take away is non-local mutable variables, those you're not supposed to have with these things. So basically, we have a restriction of things, and it's at the same time quite powerful with a proven track record in security. So for instance, if you look at supply-side attacks today, people say the gold standard would be to have essentially enforced capabilities everywhere and do it in hardware because we can't trust our software, unfortunately. So then you have things like Cherry and architectures like that, which give you some hope that you might be able to combat that. So capabilities are the gold standard in security. So why is not everyone using them today? And there are several problems with capabilities. One is, well, to use them, you need a memory-safe language, and that's, of course, already a big jump compared to C, C++, but we are not in that camp. In Scala is of course, memory-safe. But there's still problems. There are other problems. The first is they typically, when you have to pass all these capabilities around, it gets very tedious very quickly because typically you get them from your main program that tells you roughly what the whole program can do, and then you refine them and you pass them on to the leaves where things actually get done. Lots of parameters to pass around, very long call chains. And the other thing is they're actually not, they could also be safer. In particular, there's this problem of capability revocation. Normally, when you give someone a capability, then that entity can hold on to the capability as long as they want. They have it now. They can pass it to others. They can use it. So if you want to say a capability should have a limited lifetime, let's say I give you the capability to perform this operation on behalf of me, and once you're done, you shouldn't have it anymore, then there's really no good way to do that. The way that is proposed in the classical capability literature is basically to equip the capability with a switch that you can turn it off. So basically the one who grants the capability, after the call is done, it turns off the capability, which means that if somebody else wants to reuse the capability later, it's a runtime error. So it's basically a dynamically typed version, but we like static types. We like static guarantees that this wouldn't happen. So the original object capability model is untyped, and a lot of the work has been done in an untyped setting. In JavaScript, for instance, JOE was an important language for that. But I believe types can bring important improvements, namely, we can pass capabilities implicitly, we can generate them based on the type, and that makes them a lot more convenient, and we can track what capabilities we have in that type, and that makes them safer. And both of these things work really well for Scala'3 because Scala'3 already has the mechanisms to do that. So Scala'3 has using clauses, which is the modern form of implicit parameters. So it means we can pass capabilities really with very minimal boilerplate. And it has path-dependent types, which means that types can refer to program variables and values and parameters and the like. And that we also need for capabilities, because in the end, a capability is a program value. It's typically a parameter, so we need to be able to talk about that in a type. And interesting. Okay, cool. So let's talk about how we could model some of these reactive things as effects. So typically effects that we have are I/O, logging, mutation, but there are also control effects like error handling or async, and I want to talk about those. So how can we handle an error handling, which is typically done with an either or something, or a future, which is typically the abstraction for async, in a direct style using capabilities. So let's take a step back and say, well, how do we do error handling in programs? It's a big issue, and people really don't know how to do that. Some propose you should use a sum type, like an option, or either, and use pattern matching with that. Pattern matching gets clunky quickly, so how about sum types with a for expression, so monadic bind, or exceptions. So composition can be a pain for option and either. Composition with other monads can be a pain if we do monadic bind. And exceptions, the follow-on question should be, do you want checked or unchecked exceptions? And depending whom you ask, everybody says, well, yes, of course one or of course the other, but both can be very problematic. What about async, concurrency, reactive programming? Should we have callback futures? Well, that gives you callback hell, we know that. Monadic futures, like we have in Scala, is better, but again, composition with other monads can be a pain. If you want to have a list of futures of an either, then if you want to mix these things up, it gets very complicated very quickly. Async await is an improvement there, so we have this async await macro that does that, but it doesn't work well for higher order functions. Coroutines and virtual threads, yes, but that's imperative. Again, we have access to essentially concurrency and cancellation without putting that in the types. So what I would like to, for errors, is something like Rust's question mark, but a bit more powerful. So here's an example to go from a list of, in this case, results to a result of lists. I have a function all okay. It takes a list of results and gives me a result of lists. And what I say, well, I return a result. So this is result colon, and then I just want to go through my list and map every result I get with the OK function. And that would just give me what's in the result and return it in the list. So some explanations. Result colon, that's just function application in Scala'3. So I can have a function, and I write a colon, and then I put an indented block, and that's the argument. So .OK is like .get, but .get would crash if the enclosing result is an error, whereas .OK would essentially return the error to the enclosing result. And .OK works unlike, unlike Rust's question mark, it also works in arguments of higher order functions such as map. So here we see that this .OK is an argument to map, which I couldn't do in Rust. Question mark wouldn't be in a legal place here. Okay, so what about async? What I would like, so here's another example. I want to weight a list of futures. So I have a list of futures that all will give me something in the future at some point. And I want to give you a future of all the results. And if any of the futures fails, I want to give you that failure as soon as it comes. So the way I want to write that is I want to say future of, go through the list and map it with await every future. And that should be all. And again, await should also work in arguments of higher order functions, which our Scala'2 currents async await does not. So the await cannot be in a higher order function, but now here it can. Okay, and await should also be usable outside future blocks. So I should just say, well, even if I don't construct a new future, it should be able to say, well, I have a list of futures and I want to give you a list of the things that are in there. Or throw an exception if one of these futures fails. And that should be possible by just writing the same thing, but now it has essentially a capability to do this. So this async is essentially a thing. And yes, you can do async stuff. You can suspend on a computation. So that's a capability that allows to await. Okay, so now let's mix these things up. Let's wait. Let's do errors plus async. So here's the thing. We want to await all results. We have a list of futures of results, and we want to give you a future in the future of a result of all the successful outcomes of the parameter futures. Or if any of these fails, we want to give you the error result. So how would I do that? Well, it's really like Lego. I say, well, I need a future, so let me do a future colon. And then I need a result, let me do result colon. And then I need to go through the thing that I'm given, that's an FS. Well, it's a list of futures, let's map that. So what we get is a result, so let's map that with a weight. What we get is a result, let's apply the .OK for that, and we're done. So this is really like baby code. It's super simple, and this is the same which causes major headaches when you do monotransformers or things like that, where you say, well, if you're not a seasoned category theorist, then you have no hope to do any of this thing. Okay, so what is that? So this is actually quite close to algebraic effects. You can see it if you squint your eyes the right way. You can see there's algebraic effects. So each of these things is a prompt, a future, and result, which essentially represents a handler, and then each of these operations is an effect. So a prompt provides a capability, and an effect uses it. And we just follow the shape of the result type with the prompts. For each constructor in the result type, we give you a prompt that produces values of that result type. Okay, that just looks super simple. Is there a catch? And yeah, well, in fact, it is not that there can be problems. So to experiment with that, let's just turn it around and say, instead of future of result, we now do result of future. We say, well, okay, so we should be able to do the same thing. We have result, future, fs.map, okay, await. Does that make sense? That makes no sense, actually, because we shouldn't be able to break out from an async context, which is this future, to produce a result. basically here the result says, well, give me something which is an error or something which is okay. Here the thing that is okay is a future. You get a future. But in the middle of running this future, I changed my mind and said, actually, no, 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 it's not a future, it's the error. So I can't do that. I have already defined what the result is. Or otherwise put, basically, you would have a control flow that goes out of the future directly into the result, and that's a no-no for futures. Futures have to encapsulate all their control effects in their result. So we want the type system to catch this error, because if we would allow you that, then what's the point of capabilities? And in fact, the type system that we have will give you an error for this. So the 10,000-foot view of this situation is monads don't commute, and that makes them very hard, because if you want to compose monads, then you have to go to more complicated stuff like finite rectangulars or monad transformers. Effects in general don't always commute, but often they do. Capabilities as arguments to functions do commute, so that's always fine, but not all combinations of prompts make sense. So this combination made sense, and this combination didn't. So what we want the type system to flag an error when the prompts are introduced in the wrong order. Okay, and that we use the capabilities for that. So if we take a step back, what capabilities and effects, what their relationship is essentially instead of having an effect here where I return an either error or t, that's a typical effect, I give you just the t, I give you the success case in the case, and I pass as an implicit parameter a capability to raise the effect, in this case to raise an error. So the error goes into the parameter of the function. So why does that matter? Is it just pushing around symbols? It matters because it actually solves a very important problem, which is the effect polymorphism problem. Effect polymorphism problem says that unlike other effects, effects are transitive. So if I have a sequence of functions that call each other, and the last function has an effect, like one of these, then the first function will have the same effect. It has the effect of everything that it calls. And that's not the case for normal types, that you say, essentially anything that I accumulate along the call chain will become my own type. And that means that it's very complicated. If the call graph here is dynamic, like if you have virtual methods or higher order functions, then how do you represent what the effects, possible effects of the first function are? And that's the effect polymorphism problem. So a very simple case, map is always the simplest. Map on a list. So map on a list is written like this in Scala. So if I would write it with effects, like the effects like in Katz effect or things like that, then I would represent the effect as a higher kind of type, f here. I would say, well, my function now is a function from a to f of b, so where f is this unknown effect, what I have. It could be IO or either or whatever. And I give you back an f of list of b. And that becomes a lot more scary. And secondly, I noticed that I need to have two maps, map and map f. And that means I need to do that for essentially everything where I can have effects, which is basically everywhere. With capabilities, it's a lot simpler. In fact, with capabilities, nothing changes at all. I have exactly the same signature of map as before. So how can that be? So it can be because now A double arrow B is a type of impure functions that can compute any capability as a free variable. And we also have a type A single arrow B, like what you see here, for pure functions. So pure functions cannot capture any capability. A pure function is a subtype of a double. A single arrow function is a subtype of a fat arrow function. Correct. Yeah. 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 Okay. So in a sense, we waited with Scala to reserve the pure single arrow until we could have pure functions, and that's why Haskell uses single arrows and Scala uses double arrows historically. No, it's just an accident. Okay, you could say good, fine. So this is amazing that we can do this, and the fact it works is that basically the function here captures the effect it can have in this double arrow. It says I come with the effect that I have, and And therefore, the map function doesn't need to be concerned. The map function will just execute any effects that its argument will execute. So in our terminology, map is actually a pure function. It doesn't have any capabilities by itself, but it might be passed arguments that do have capabilities, and it is allowed to execute them. There's a catch, however, and to look at the catch, we can do a simple example of a try with resources pattern. So we have this, this program with file. So it takes a body that wants a file and does something and returns a T. And we create a file, a log file, and we pass it to the body, and the body would then use this log file for its logging. And once the body is done, we close it, and we return the result. And the usage would be like this, with file, colon, f, arrow, f dot write, OK, right? So we've just passed the function to with file, and the logging is handled by with file itself. Can you see a problem here? Well, the problem could be that body might return a closure, the function itself that accesses log file after it is closed. So for instance, like here. So we have with file f, and then we pass here the function. That's how an added function to say, well, when the function is called, then let's write unlike to the function. And that doesn't work, of course, because by the time this thing gets returned, the closure gets returned, the file will be closed. And when we want to write afterwards to that, when we apply the closure, we want to write to the file it's closed. So that would be an error that we have to prevent. And to do that, what we need to do in Scala is we need to add a single letter, which is this up arrow here. So we write up arrow for the file thing, and that would classify the file thing as a capability. We now say, OK, so this thing is a capability. And otherwise, with file is as it was. And then if somebody tried the bad thing, the problematic thing, then you would get an error, which is you have to sort of walk through the error message. But the important part here is note that capability F cannot be included in outer capture set S3. So basically, we have a capability that we essentially want to include in this parameter here, and we can't do that. Okay, so the mechanics of how that works is we have these new form of types, which are called capturing types, where T is a type and C1 to Cn is a capture set of capabilities, and these capabilities, they're just regular program values. And the capability, a regular program value is made into a capability because it has a capture set. So every capability gets its authority from some other more sweeping capability that it captures. And there's a root capability cap from which otherwise all others are derived. So that's the way it's set up. And there's a paper later on at Uppsala by Yichen, and he's the speaker on what's in the box. And there's a slight change of perspective in that paper. So cap is now no longer a root capability, but there are several one of them. Basically, each one of them is another existential or universal quantifier. So that's essentially the essence of Yichen's paper on Thursday at Uppsala. But we still write it the same way. So basically, we write the source language the same way, but the foundations underneath are a bit more refined and closer to traditional logic, let's say. So there are abbreviations. So when we write this ski hat, that's really just saying ski hat with hat in the capture set. When we write a function arrow followed by a capture set, that's really the normal function arrow with the capture set at the end. And when we write the double arrow, it's really the arrow. So the double arrow means it's a function that captures an arbitrary unknown capability. Okay, so if we do this in practice, then we can turn it on like this. We have a language import. You have to write import language experimental capture checking, and you then have essentially everything. The separate compilation is supported, and the notational overhead seems to be quite reasonable. So to give you an example of that, here's the list API in our standard library. That's what it looks like. So most functions up here are exactly the same as before. The map function is exactly the same as before, as I've shown you that. In some cases, I need to do a little bit more. So, for instance, for the flat map function, I say, well, yeah, okay, so here this function that I pass to flat map, it can have effects, but so can the iterable ones that I return in the flat map. So basically, flat map takes, or let's say concat is the same thing. So I concat iterable ones to this collection, and that iterable can have side effects. As I traverse it, concat can have side effects. So to capture the old behavior where side effects are possible, I can do that by just adding the hat here. And that gives us also a fine-grained control whether arguments should be pure or impure, because I could also drop this thing, or I could have a map, let's say a parallel map with a single arrow, which says, well, to a parallel map, you have to pass me a pure function. I can't do a function that has side effects. Things get a bit more interesting when you have a lazy collection, like an iterator. So for an iterator, iterators are things where the map would create another iterator that essentially is evaluated only when I call next on the iterator, right? So now this map function would return you an iterator that says this iterator will actually hang on to the current iterator, because next calling on the mapped iterator calls next on the current one, and it will also hang on to the function f, which could have a side effect. So I know very precisely what things are retained in the results of these things as capabilities. So transforms of iterators get capture annotations that tell us about latent effects. And I would argue this is what you want. If you have just an iterator, the next question should be, well, an iterator, yeah, but it can do what? Right? So you want to know what it can do, and here that it does precisely that. So basically the annotations stay out of your way when they would be trivial, and they tell you precisely what you want to know when they're not trivial. Okay. That's, sorry, I did. Okay, so that was the current state. No, so the current state is that the library that I've shown you will actually ship. It is in the nightlies. Standard library is now fully capture checked, so you have the annotations in the library, and we are also about to release capture checked versions of other things which are not yet in the standard library. One is steps, which is an incubator for a set of utilities such as result that I've shown you, and the other is gears, which is our concurrent programming with direct styles, futures, and channels library. Okay, so what are we cooking now that we're done with this? So the next steps is that we have seen that capabilities are, so far we have seen that capabilities are resources with limited lifetimes, but they can also do more. And another question is, can they enforce sharing restrictions? So what we want to do is exclude global side effects, avoid data races, fearless concurrency. That means we want to have capabilities that mediate access to immutable data structures. And that's another project, a sub-project that we started. It's called Project Capybara, Capabilities for Mutation. Capybara is because they're nice animals, and also if you pronounce it the right way, so it's sort of capybara, so borrowing this sort of thing. So anyway, so that's the new project. This thing was ChatGPT generated after some input so from the oldest Western depiction of a capybara, which is here. So the banana becomes the lambda, and the palm tree becomes the Scala thing. So I give you just a quick run of what this is. So here's a matrix multiply, matrix A, B, C. The question is, what is input, what is output, which arguments can be shared, which arguments are unique. It doesn't really tell you much, right? So this sort of thing, but that's sort of the things you have to contend when you have operations like that. So what we can do now is we can have first define a matrix to be mutable. So a matrix extends mutable. And then furthermore, we define the method that sets an element of the matrix to be an update method. So that's two things. And then in the mutation, what we do is we give you the output with a hat. So that says this thing is writable, and these things, A and B, are only readable. So the hat now means it can be modified. It's a capability allowing an effect. And the fact that we interpret it as that has to do with the fact that it's on a matrix and matrix is mutable. So if a capability is on a matrix and matrix is mutable, it means it's mutation. And it also means it doesn't share with anything else that can be accessed, and that's the separation part. So with the separation checking that we have, we can now say that if we multiply matrices A, B, and C, that's okay. But if we multiply A, B, B, that's not okay, because B cannot essentially has a hat here and cannot be referenced separately. On the other hand, multiplying A into C is okay, because the first parameters here, they're just passed as normal parameters. And that requires currently a separate language import for separation checking, because that's work in progress and not everything is checked out yet. And what we also have is we can do that for linearity. So Scala has these buffers, and buffers has this plus equals method. And plus equals is sort of like concatenation, but it's imperative. And we want to protect ourselves better against side effect of these things. So an example here would be we create a buffer and we append some elements to it. And the result is a new buffer C. And now we append a further element to C. And, but now the last one should be an error, because we append something to the original buffer, but the original buffer is now aliased in first C and then D. So appending something to the original buffer would have a hidden side effect on these things here, because they all share the same buffer. There's no copying here. So what we're after is a linear type system, and that's enforced by this consume thing. We can put consume on a def or on a parameter, and that means once we've used it, then it's no longer available. So if we put it on a def, it means that the receiver is no longer available. So here, the B plus equal would be consumed, and that means we can't use the consume afterwards. So to conclude, capabilities are super versatile because they can model global effects, control effects, permissions, mutations, information flow. The list goes on. It's really a Swiss Army knife of things in software security and trustworthy computing. The main value proposition of Scala is to be both safe and convenient, and I think with the right types we can make capabilities safe and convenient. We can use implicit parameters. We are using clauses and capture sets to model the retained capabilities. So to find out more, there's a paper in ACM Toplas 2024 that we saw the foundational paper on this. It's called Capturing Types. There was a paper at UPSLab about our first steps into separation, which is not what you've seen. That was like a preliminary thing. And there's a paper at this UPSLab on what's in the box about essentially the current calculus that underlies our system. And there's an implementation in 3.8, which is due later this month. If you look at DOTI, EPFL docs reference, you already get the documentation of the current nightly versions, and that's probably the best place to start with if you want to play with it. Thank you.
All right, I think we have time for a few questions.
Just curious, is Scala the first language to combine capabilities and effects like that? And how does it compare if there are others doing similar things?
In general, yes. In general, I think it's the first, well, I'm not sure about small research languages, but the first sort of language in actual use that does this, I believe, yeah. Okay. Yeah. History in typing, 25 years, I would say. And essentially, the meaning here is capability is another layer of our type system, but they are essentially types only, sort of like regions or things like that. And I think reference capabilities are of this thing. It's a type systematic abstraction. Here, our capabilities are really regular program values. So in a sense, they are more direct and more easily to understand and to manipulate because you have the full power of the term language for them. That said, there are also some tweaks where object capabilities are a problem. For instance, the way I presented them, they're always real program values. So they get passed, they take up space, they take up time to pass them, and you don't need that always. So we have another thing which is in the next talk after this one about how we can have erased things, and then they become more like reference capabilities. So they're object capabilities, but we have an erased modifier that says these things are not present at runtime. So and there's a type system that checks that that's possible.
Yeah, but maybe we can keep the question for after because we are running late. Yeah, I'm sure Martin will be available at dinner and maybe at the later session today. So